Since the turn of the century, wire-bound containers have been providing protective packaging for fresh fruits and vegetables, meat, poultry, seafood, and a wide variety of industrial and military products. These containers are specifically engineered to meet a product's requirements for protection, high stacking ability, or ventilation and drainage for melting ice in the case of food products. Wood, which is a renewable and manageable natural resource, and wire are the principal materials used in making wire-bound containers. While hardwood varieties of timber such as black gum, sweet gum, and poplar are the most common woods harvested for fabricating wire-bounds, red and white oak, tupelo, maple, cypress, and cherry are also sometimes utilized. After selected trees have been cut down, several logs at a time are picked up by skidders and dragged through the woods to a clearing, which could be located up to half a mile away. Here, logs trimmed of excess limbs are cut to desired length. Those logs which are more than 10 inches in diameter at the small end will be used for veneer stock and are cut to 14-foot, 16-foot, and 18-foot lengths. Smaller diameter logs between 7 and 10 inches on the small end are designated for cleat stock and are cut to 14.5-foot lengths. The operator of the knuckle boom loader, who also operates the saw, separates the logs and cuts them to prescribed lengths before loading them onto a truck. On arrival at the mill, the truckload is weighed and the logs are entered in inventory. Then it is unloaded in the yard by the same type of knuckle boom equipment used in the woods to load the truck. The logs are then separated by wood species using a heavy-duty fork truck. At the sawmill, logs designated for cleat stock are brought to and placed onto a live log deck. Cleats are the component of a wire-bound container which form the framework and to which the faceboards are stapled. The logs move along this deck to a second conveyor, where a cut-off saw cuts them to 88-inch lengths. These logs then proceed to a head-rig circular saw, which cuts them in half. A horizontal resaw then cuts boards from the flat surface. The remaining upper portion of the log sections are conveyed on a carousel system, which keeps returning them to the resaw until the log's maximum utilization has been achieved. The resultant sawn boards are then removed and stacked in such a manner as to allow maximum airflow around each piece of lumber for air dry. These stacks are removed to an open outdoor area where they remain for a period of 60 to 90 days, depending upon the amount of moisture content desired. Stacks of air-dried lumber are delivered to a high-speed planer, where the boards are planed to the proper cleat thickness. As the surfaced lumber leaves the planer, it is directed to a gang ripsaw, where each board is ripped into the desired width of cleat stock, 11/16 inches in this instance. This cleat stock is then directed to a multiple cross-cut saw or equalizer that cuts the stock to predetermined lengths. At this point, the material is graded for quality. Those not up to standards are removed and conveyed to the chipper or used for boiler fuel. The good cleat stock is conveyed to the tensioner, where it is mitered, cut at prescribed angles, and notched. The processed cleats are then bundled and palletized, ready for use at the stapling machine. Logs that have been selected for use as veneer stock are conveyed to a debarking machine, which removes up to 90% of the bark. The purpose of debarking is to remove dirt and other material in order to reduce excessive wear of the lathe knives and to produce quality chips. The debarked logs are sawn to proper block length as required by the containers to be manufactured. Blocks are centered in the lathes either manually or mechanically and are rotated against the lathe knife and back roll simultaneously. A back roll is used to score the block as it rotates, thus economically producing slats of a uniform width. Spur knives also score the rotating block, thus yielding slats of equal length. Single or multiple slats can be produced. Below the lathe, veneer slats are graded, and any poor quality material is discarded to be processed into chips. The resultant acceptable slats are accumulated in bins, which are then transferred to the dryers. Some dryers are steam operated, while others are gas fired. The steam is generated by boilers fueled by log waste material. Slats are placed on the dryer's conveying system. The speed of the dryer is controlled based on the thickness of the veneer and the final moisture content desired. With this high-speed dryer, proper drying can be achieved in between 4 and 9 minutes. When dried, 10 to 18% moisture content, the veneer is neatly bundled and stacked on pallets for transfer to the warehouse or temporary storage area for its subsequent use at the stapling machine. At this point, cleats have been manufactured, veneer has been cut and dried, and we're now ready to fabricate wire-bound containers. A stapling machine unit is comprised of an automatic stitching machine and a rock fastener machine. This unit is versatile, capable of manufacturing a wide range of container sizes and designs. Material for fabricating the containers is supplied to the crew at the stapling machine. Cleats and slats for making standard containers can be positioned in the stitching machine's conveying system automatically by cleat hoppers and slat feeders. This function can also be performed manually with the addition of several workers. The stitching machine conveys cleats and slats under the stapling heads. Staples, which are automatically formed from coils of stapling wire, are driven over binding wires into the slats and cleats. At times, containers are printed during fabrication to identify the type of container and/or the manufacturer's name. Some manufacturers pre-print this information on their slats. This container shown being fabricated is a corn crate. At the rock fastener machine, the closing loops are formed. It takes only approximately 1.5 seconds to cut the binding wires, form the loops, and drive and clinch the wire prongs into the leading and trailing slats of each container. As the wire-bound blanks exit the rock fastener machine, ends that were previously manufactured on a similar machine unit are then attached. Crate ends can also be secured by a mechanical end attacher. The unitized containers are then bundled and palletized. Bundling can be done by automatic machine as shown, or by hand. These bundled wire bounds are then loaded onto trucks or freight cars for delivery to customers. Note that they are shipped in a knockdown form to conserve valuable space during shipping and storage. Containers such as these are used at a grower's packing house or in the field for packing fruits and vegetables. In an industrial wire-bound manufacturing operation, surface dry lumber is delivered to the plant from the lumber yard and placed on conveyors, which transport it inside to the cutoff department. This material, which already has been processed to desired thickness, will be used to make cleats for various wire-bound containers. At the cutoff saws, the material is cut to predetermined lengths. The material then goes through a rip saw where it is cut to width. When properly sized to length and width, the cleats are diverted to 2 lines leading to tenoners, which miter the cleats. The resultant chips, off-grade, and scrap material are used to fuel the boilers. In most industrial wire-bound plants, faseboards are produced in the resaw department. Blocks of timber called cants are cut to length and width, then fed through a gang rip saw to produce multiple slats of desired thickness. In some plants, faceboard material is delivered to the cutoff department already cut to desired thickness. It is then cut to length and proceeds through rip saws which cut it to desired widths. As the boards emerge, they are inspected and graded. Throughout the entire material processing operation, rigid quality standards are followed. Because of the greater size and complexity of industrial wire bounds, compared to the fruit and vegetable crates shown earlier, cleats and faceboard material are placed manually into the machine's conveying system. This container is used to ship automotive engines. This pallet container, which has diagonal faceboards, is designed to prevent racking of the package and its contents during shipment. Veneer is often used as faceboard material for some industrial applications. This container is designed for insulators. A small plywood container, this one for 60mm mortar ammunition, is shown being fabricated. Ends for this container are shipped separately and are attached at the munitions packing plant. Printing can be done on the faceboard material prior to box fabrication. In this instance, faceboards are being printed according to government specifications. These wire-bound containers are representative of what you've just seen being manufactured. fruit and vegetable crates, military packaging, seafood containers, and industrial packaging for sinks, bathtubs, water heaters, and pallet containers for bulk shipments of myriad products. Mass-produced, these wire-bound containers are versatile, strong, even in rain or high humidity conditions, lightweight, thus using much less material, economical, and they provide excellent product protection.